This is your presenter Asloob Mudassar, and I am presenting slide number 100 of the course on laser physics. The question is, beams from diode lasers have elliptical cross sections. It is desirable to convert the elliptical cross sections into circular cross sections for pumping an active medium rod. How is this transformation accomplished? The answer is, pumping diode lasers normally have elliptical shaped beams which need to be converted to beams of circular cross sections before it is used to pump an active medium rod which is in the shape of circular cylindrical rod. The ellipticity of the beam is changed to circular beam using a combination of a spherical lens and an anamorphic optical element. Look at the figure 1. The caption of the figure is beams originating from the exit window of a single strip diode laser. This is the exit window from a single strip diode laser, and you can see that the two beams have been shown. One is in dotted, the other is in solid lines. The dotted lines are the horizontal beam because they are parallel to the longer dimensions of the exit window, and this is the beam which is vertical beam is coming out from the shorter dimensions. That is why it is more diverged, and the divergence of this beam is larger than the divergence of the horizontal beam. So this is forming a vertical beam. The divergence angle that I am going to refer in the next few pages, the divergence of the vertical beam will be indicated by theta perpendicular, whereas the divergence of the horizontal beam will be indicated by the angle theta parallel. The caption of the figure is beams originating from the exit window of a single strip diode laser. So you see that we shall be talking about two beams from the exit window. One is the parallel beam, which is shown in dotted line forming a horizontal beam, and the other is the solid beam represented by the solid arrows forming vertical beams coming out from the narrow directions of the exit window. So more diverged, and the divergence of this vertical beam will be indicated by theta perpendicular, whereas the divergence of this horizontal beam will be indicated by theta parallel. Now you see that the divergence of these two beams is different. The divergence, that is, the vertical beam is more diverged as compared with the horizontal beam. So this has an elliptical shape with major axis along the vertical beam and the minor axis along the horizontal beam. So what we this elliptical beam is what we want to convert into a circular beam. That is, the both beams should have the same divergence, so forming a circular diameter, so that we can use this beam in the pumping process for uniform delivery of power. Beams originating from the exit window of a single strip diode lasers are shown in figure number 1. This is what we have discussed: vertical beams and the horizontal beams. The beam in the solid is a vertical beam which is more divergent and lies in a plane perpendicular to the plane of the junction or the plane of the exit window. The dotted line is the horizontal beam and lies in the plane of the junction. The two beams combine to yield resultant elliptical shape of the beam. This is what I have discussed with the relevance to the previous figure. That is, with the relevance to this figure, the paragraph has explained everything. The setup for transforming an elliptical shaped beam into a circular shaped beam is shown in figure number 2. So let's look at this figure number 2. So you see that this is a diode laser, and of course the two beams are coming. One is shown in dotted line, which is the horizontal beam, and the other is shown in solid, which is the vertical beam, as I have discussed with the relevance to figure number 1. And you see that a lens L1 of a focal length f1 has been placed. This is a cylindrical lens, so it will only act on the dotted lines, that is the horizontal line, and will try to make its diameter equal to the diameter of the vertical beam shown in solid line. And these two beams now have the same diameter, will pass through the anamorphic expander. The anamorphic expander will make the diameter of the two beams equal to each other. So the dotted lines, which is the horizontal line, which is the horizontal beam, and the solid lines, which is the vertical beam, these two beams have the same diameter at the exit of the anamorphic expander. And you know that I have also shown the shape of the beam at before the anamorphic expander. You can see that you have the parallel beam and you have the perpendicular beam shown over here, forming a major axis and the minor axis. So an elliptical shape is formed over here. And after passing through the anamorphic expander, you can see that the parallel beam and the perpendicular beam has been shown, and both are equal in radii or in diameter, and forming a circular spot of the laser beam. The caption of the figure 2 is a schematic diagram of transforming an elliptical beam into a circular beam. So let's read the relevant paragraph. The elliptical beam becomes much elongated along the perpendicular direction due to much greater beam divergence. To stop further beam elongation, the beam is collimated using a short focal length lens and high numerical aperture spherical lens of a focal length f1. So we can use a focal length f1 in order to control the divergence. So this is a lens L1 is a lens of a spherical lens of a focal length f1, so that it can control the divergence of both the beams. And once the further divergence of the beam is stopped, it will have to pass through the anamorphic expander. Let us assume that the perpendicular beam is 4 times more divergent than the parallel beam. That is, theta perpendicular is of the order of 4 times the value of theta parallel, where theta parallel is the divergence of the horizontal beam shown in dotted line in reference to figure number 1, and theta perpendicular is the divergence of the vertical beam shown in solid in figure number 1. So these two divergences are related, for example, through a factor of 4. The dimensions, okay. The dimensions of the beam after passing through the lens L1 will be, the dimensions of the D perpendicular will be 2 times of F1 tan of theta perpendicular, and the dimensions of the parallel beam will be equal to 2 times of F1 tan of theta parallel. So if you multiply the two, so D perpendicular multiplying by D parallel will be equal to 2F1 times theta perpendicular multiplied by 2F1 times theta parallel. So these are the dimensions of the beam that I have shown after passing through the lens L1, where F1 is the focal length of the lens L1. As the divergence is small, we can write that tan of theta is approximately equal to theta, and D perpendicular to the D parallel, this ratio is of the order of 4. To transform the elliptical beam into the circular shape, an anamorphic beam expander with a beam expansion ratio 4 to 1 and 4 to 1 the same as parallel to perpendicular, or we can write that 4 to 1 is equal to parallel to perpendicular is inserted in the path of the beam. So this is the expander that will be inserted in the path of the beam. This type of a beam expander will expand the beam in the parallel direction by 4 times the beam expansion in the perpendicular direction. The simplest beam expander may consist of a combination of two cylindrical lenses L2 and L3 in the confocal arrangement as shown in figure number 3. So let me explain figure number 3. So you see that the two beams are incident on the cylindrical lens L2. One is shown in the dotted, which is the horizontal beam, having smaller divergence, or we can say it is a parallel beam. And the other beam, which is shown in the solid, is the vertical beam. Or we can say that it is the beam perpendicular to the junction. So it will pass through the lens L2, having a focal length f2. And then of course the beam will converge, and then it will diverge towards another cylindrical lens L3. Both the lenses, that is L2 and L3, are arranged in the confocal arrangement. That is, the focal length of the lens 2 is over here, and the focal length of the lens 3 start from this focus point. So that is, this focal point is the common focal point for the lens L2 and for the lens L3. So after the lens 3, you can see that the horizontal beam shown in dotted line and the vertical beam shown in the solid line both have the same diameter after exiting the lens L3. The caption of the figure is anamorphic beam expander based on two cylindrical lenses of different expansion ratios along the two perpendicular directions. So you see that these two lenses have different expansion ratios along the two vertical directions. So one controls the horizontal beam, the other controls the vertical beam, and then makes their diameter equal to each other. And so after exiting lens 3, both the horizontal beam and the vertical beam, they have the same diameter. So this is what the purpose of this beam expander, consisting of two cylindrical lenses L2 and L3 arranged in focal arrangement. That is, L2 and L3 both have the same and common focal point located in between the two lenses. So you see that with this arrangement, we can make easily the diameter of the two beams equal to each other. So this is very accurate when we are talking about a single strip diode laser. But what about if we have a diode array or a diode bar? So let's discuss about such a problem. The anamorphic beam expander will expand the beam 4 times along the parallel direction if f3 over f2 is equal to 4. So you see that I have also given the ratios of the focal lengths. That is, the focal length of f3 to the focal length f2 has a ratio equal to 4. No expansion will occur along the perpendicular direction. The outgoing beam from this expander will have circular cross section, that is, apart from parallel direction, the expander will behave as a plane parallel plate for the beam which is perpendicular. The lenses L2 and L3 must be well corrected and diffraction limited. So you see that this beam expander is actually controlling the dimensions of the parallel beam to 4 times, because the ratio or the magnification of the system is 4 times for the parallel beam. So the diameter of the parallel beam will be increased. It means that its divergence will be decreased by 4 times. So if you increase the diameter by 4 times, the divergence will be decreased by 4 times. So then ultimately you have the two beams, that is the parallel beam and the perpendicular beam, both having the same diameter. So this is the description with respect to the figure number 3. Now the second method of converting or transforming the elliptical beam from a single strip diode laser to circular beam is through an anamorphic pair of prisms. The first prism is arranged in such a way that the beam exits the second phase of this prism normally. That is, without undergoing any refraction at the second interface. So this is, you can see from the figure, that is, this is the incident beam of diameter d1 from the single stripped diode laser, and this is incident at an angle theta I. You can see that this beam makes an angle theta I with the normal to the prism surface, to the first surface of the prism, and then you see that the beam is refracted inside the prism with an angle of refraction denoted by theta r. So theta r is again the angle measured with the normal to the first surface, and you see that we have chosen theta I in such a way that the beam which is refracted inside the prism is incident normally to the second surface of this prism. So this is the second surface of the prism on which the beam is incident normally. So this is the choice of theta I makes it to happen. So you choose theta I in such a way that the beam within the prism becomes normal to the second face of the prism. So no refraction will takes place and the beam will pass straight without any deviation. And then this beam, which now has a diameter equal to dr, obviously the diameter dr is greater than the diameter di, and then you see that this beam will incident on the second prism. Again, the second prism is arranged in such a way that the beam is incident at an angle theta I to the first surface of the second prism. And again, you see that due to this one, the two beams are identical and the angle of incidence is the same as for the prism one. Of course, the beam which is refracted inside the second prism will travel normally to the second surface of the second prism, and the beam will pass straight with a diameter d naught. And you can see that here we have the dotted line and the vertical lines, that is the horizontal beam and the vertical beams shown in the solid line, the horizontal beam shown as the dotted line. Both beams have the same diameter equal to d naught. Alpha is the apex angle of each prism and n is the refractive index of the prism. And the caption of this figure 4 is anamorphic beam expander with the two identical prisms of refractive index n and apex angle alpha. So let me read from this paragraph that the first prism is arranged in such a way that the beam exits the second face of this prism normally, that is without undergoing any refraction at the second interface of the first prism. So we'll pass straight, and similarly for the second prism, for the second phase of the second prism, the beam is also incident normally and of course will go straight without any deviation. Assume that theta I and theta r are the angles of incidence and refraction at the first face of the prism, and that the beam enters the first interface with the diameter di and leaves the second interface with the diameter dr. Then the magnification m through the first prism is given by. Now you see that what will be the magnification through the first prism? That is what we can write as given in equation number 1. So the magnification of the system is m is equal to dr over di. The ratio of the outgoing beam to the incident beam is equal to cos of theta r over theta I. This relation is what you can find out very easily from this diagram. You see that we are now want to correlate cos of theta r with the cos of theta I, and also through the diameter we want to relate diameter di with the diameter dr. You see that this you can see that this normal line is intercepting the first surface of the prism at a point over here. This is the point, you see. From this point to this point where the solid line hits the first surface, this distance is common at the first surface for the two right angle triangles. So draw two right angle triangles with the hypotenuse equal to this before the first prism and inside the first prism, with the di as a perpendicular to the of the first of the right angle triangle before the first face, and after the first face draw the right angle triangle in such a way that the hypotenuse is this one, the common hypotenuse of the two right angle triangle, and then the perpendicular has and the perpendicular equal to dr. So if you draw two right angle triangles at this interface with the hypotenuse common lying at the first interface of the prism, then of course you can find out very easily the relationship between the two things, that is dr over di is equal to cos of theta r over cos of theta I, as shown in equation number 1. So this will give you the magnification at the first interface of the first prism. If the second prism is identical to the first prism and arranged with the angle of incidence equal to theta I, as we have discussed earlier, the beam will exit the second interface of the second prism normally with the magnification again equal to capital M. The total magnification of the anamorphic prism pair will be M square. The output beam will be parallel to the input beam but will be shifted laterally. The output beam will be circular if m is equal to 2 and m square is equal to 4. So you can see that the two beams are shifted laterally. For example, this beam is coming horizontally, and then you see that the output going beam is also horizontally moving towards the right, but you know that there is a shift between the two beams. So this beam is laterally shifted, that is the outgoing beam is laterally shifted with respect to the input horizontal beam. So this is laterally shifted, but this is not any problem. And of course the magnification of this whole system is m square. And you see that here we have assumed that the magnification due to prism 1 is m is equal to 2, and the same is for the prism 2, that is the magnification from the second prism is m is equal to 2. So the total magnification of the system is m is equal to 4. So you see that this scheme will work. The output beam will be parallel to the input beam but laterally shifted. The output beam will be circular if m is equal to 2 and m square is equal to 4. So you see that this is the condition that we are putting over here, that if you want to get output beam to be circular, we have to have m is equal to 2 and m square is equal to 4, because you know that we have the relationship that is the divergences are related in such a way. For example, you can see the ratio over here. The ratio in the radii of the two beams d perpendicular to the d parallel is equal to 4. So here we require that the magnification of our anamorphic prism systems should be equal to m square is equal to 4. Or simply m is equal to 2. So this is what we have obtained from that one. So m should be equal to 2 and m square is equal to 4. So that we can get the circular beam out of this anamorphic prism system. Now to set m is equal to 2, an appropriate value of theta I is chosen for given values of the prism refractive index n and the prism apex angle alpha. When the output beam is circular, the divergence of the two beams will be identical along the beam axis. So you see that here we have increased the diameter of the beam, that is we have equalized the diameter of the horizontal beam and the vertical beam. But you see that the divergence of the system will still be equal to the divergence of the vertical beam. That is the theta perpendicular will be the divergence of the system after passing through this prism. So you see that when the two beams, that is the horizontal beam shown in a dotted line and the vertical beam shown in a solid line, will come out from the second prism, then of course the diameters of these two beams will be equal to each other, but the beam will have some divergence, and the divergence of these two beams will be equal to the divergence of the vertical beam, that is theta equal to the theta perpendicular. The divergence of the two beams will be identical along the beam axis. A well-corrected, diffraction limited and aberration free lens L4 can be used after the anamorphic prism system to focus the beam with the circular spot onto the circular cross-section of the active medium rod placed at an appropriate distance away from the lens L4. So you can place a lens L4 after the prism system so that you can focus the beam onto the circular active medium rod, and you can place the active medium rod at appropriate distance, so that the spot from the laser beam from the diode, from this single stripped diode, should match with the diameter of the active medium rod. Now consider the case of an array of 20 diodes. That is, we are going now to discuss a diode array. So now consider the case of an array of 20 diodes, each of 5 micrometer wide and spaced center to center by 10 micrometer, forming a 200 micrometer wide active region with the theta perpendicular is of the order of theta 4 times theta parallel, where theta perpendicular is equal to 20 degree and theta parallel is equal to 5 degree. So this is what we have assumed specific values, practical values. For example, for the case of each single strip in a diode array, and a diode array has 20 single strip diodes joined together on a single chip. And the dimensions, you see that I have given 5 micron, and the separation from center to center is 10 micron, and forming the length of the array of diodes is 200 micrometer wide. And the divergence of the perpendicular beam and the parallel beam is the same as that for the case of a single strip diode laser. That is theta perpendicular is 20 degree and theta parallel is equal to 5 degree, and the relationship again is there, that is the theta perpendicular is equal to the 4 times of theta parallel. The theta perpendicular and the theta parallel for the array are the same as for the single strip diode. The divergence of the beam from the longer dimensions of the active medium from the diode array will be 40 times that of the same beam from the single strip diode. Or more precisely, you can say that the diameter of the beam from the longer dimensions of the active junction from the diode array will be 40 times to that of the same beam from the single strip diode. Now, if an anamorphic beam expander, as discussed for the single strip, if applied to an array of diodes, the output beam from the anamorphic beam expander would still be elliptical. So you see that over anamorphic prism system that we have discussed over here, or the anamorphic expander system that we have discussed earlier, that is not sufficient enough to produce circular beams when we are talking about a diode array. So still we shall be getting the beam which is elliptical in shape. So our expanders are not going to work in that case. More accurate method is based on the use of multi-mode fiber of sufficient length of core diameter of 200 micrometer coupled to the diode array. So you see that if you have a multi-mode fiber of a core diameter of 200 micrometer, you can couple it to the diode array. The acceptance angle of the fiber, denoted as theta f, with the numerical aperture of the fiber is equal to sine of theta f, must satisfy this condition, that is sine of theta f that should be greater than the sine of theta perpendicular. Here we are not talking about theta parallel, because theta parallel has a smaller divergence and theta perpendicular has a greater divergence. So we are addressing the problems of the theta perpendicular. So the acceptance of the numerical aperture of the fiber should be such that sine of theta f should be greater than, or at least should be equal to, the sine theta perpendicular, where theta perpendicular is the divergence angle of the highly diverging beam of the single mode of the single strip fiber, or the beam from the single diode. The outgoing beam from the fiber will be circular with the beam divergence, that is theta out is equal to theta f. So you see that now we are able to produce a circular beam using multimode fibers of appropriate length, and the out and the out and the diameter of the beam from the output end of the fiber will be circular. That is, the theta out will be equal to theta f, and the divergence of the beam, though circular, coming out from the fiber will have some divergence, and that divergence will be equal to the angle of acceptance of the fiber, that is the theta out of the beam with circular spot coming out from the second end of the fiber. Theta out will be equal to approximately equal to theta f, that is the acceptance angle of the fiber. You see that in this process we have addressed theta perpendicular only, and you see that it means that we have allowed theta parallel, which was 4 times smaller than the theta perpendicular, to become also equal to theta perpendicular, that in order to produce a circular beam. So here we have two beams with the same diameter, and of course the same divergence, because we have produced circular beams. That is the diameter of both the beams, that is the diameter of the vertical beam and the horizontal beam will be the same, but with the divergence will also be the same, that is the theta out will be equal to theta f. Note that theta in is equal to theta parallel. For the parallel beam, if you address only for the parallel beam, you know that the parallel beam has a theta in into the fiber. Theta in is equal to theta parallel. But theta out is equal to theta f. That is, the divergence of the theta parallel has increased, so that the two beams have the same diameter. Also, theta f, you know that is greater than theta in, because theta f at least could be equal to theta perpendicular, as from the previous equation in the previous diagram, previous paragraph we have seen that the least condition is that theta f should be equal to theta perpendicular, and you know that theta perpendicular is greater than 4 times by from theta parallel. So theta perpendicular is greater than theta parallel. That is, the beam out of the fiber is more divergent than the beam into the fiber, as far as the theta parallel beam is concerned. Because you know that for the theta parallel beam, we have the theta f is greater than theta in, because theta f will be because of the divergence of the output going beam is equal to theta f, and you know that theta f is greater than theta in. It means that the parallel beam has increased in its divergence. That is, as far as the parallel beam is concerned, its divergence has increased as far as the output beam from the output end of the fiber is concerned, and as far as the parallel beam is concerned. So the beam out from the fiber is more divergent than the beam into the fiber. As far as the parallel beam is concerned, the divergence can be reduced by using a cylindrical collimating lens to collimate the beam with the divergence theta perpendicular to the fiber diameter. So you see that in order to decrease the divergence, we can use what we can do is that we can use a collimating lens, a collimating cylindrical lens just after the two beams, so that it can only control the divergence of the theta perpendicular beam without affecting the theta parallel beam. So we can make the divergence of the theta perpendicular beam to be reduced by 4 times, so that theta perpendicular becomes equal to theta parallel. So then these two beams can be combined with can be passed through can be coupled into a fiber, so that the beam after passing through the fiber will have the same diameter. So the fiber must then be replaced with a fiber of theta, that is, the acceptance angle of the fiber can now be reduced equal to theta parallel, because now we have made theta perpendicular equal to theta parallel. So we can use a fiber with a smaller angle of acceptance. Now there is another option that here we are talking about diode bar. You see that we have talked about single strip, Diode laser for the single strip we have mentioned. You see that we have mentioned some this is the beam from the single strip diode, and we have mentioned this setup shown in figure number 2, and we have mentioned setup in figure number 4 in order to make the diameters of the two beam equal to each other. That is the diameter of the horizontal beam and the diameter of the vertical beam to be equal to each other, because this is only applicable to the single stripped diode. But you know that when you have combined many single strips to form an diode array, then of course I have mentioned the process, that is the fibers can be used, multimode fiber can be used in order to equalize the diameters of the two beams. But you know that if you are using a diode bar which is consisting of many diode arrays, then what will happen? If a diode bar of length say 1 centimeter is available as a light source to pump an active medium rod, then the light is first passed through the cylindrical micro lenses to focus each individual array of the bar into separate multimode fibers, each of 200 micrometer core diameter and numerical aperture equal to zero point 0.1. Each array is 100 micrometer in length, and a diode bar of 1 centimeter length has 20 diode arrays, and thus 20 fibers in each array are used. So you see that this diode bar now contains 220 diode arrays, and each diode array contains 20 fibers. So you see that in front of each diode array, we can use a fiber of 200 micrometer core diameter, having acceptance, having a numerical aperture equal to 0.1. And then of course you can collect these, you can use 20 fibers for each of the array, and then you can collect these, then you can collect the data from, then you can collect the light from each diode array, and then you can combine those to form a single beam. The output light from the fibers is then collected, that is collected from each fiber and imaged onto an active laser medium. So you see that as far as the diode bar is concerned, this diode bar here we have given an example that it consists of 20 diode arrays, and each diode array has 20 fibers. Then of course in front of each diode array we can use 20 fiber systems, each of 200 micrometer core diameter of numerical aperture 0.1, and we can collect the light from each diode array, and then of course these 20 diode arrays can then be combined and focused or imaged onto an active laser medium to focus the beam in order to pump the laser active medium. So you see that we have described single step diode laser, we have described diode array of 20 single step diodes, and then we have discussed the diode bar consisting of 20 diode arrays, and each diode array consisting of 20 single step diode lasers. And then we have suggested the method how we can combine, how we can collect the beams from this one and can focus onto the active laser medium for the pumping processes. But you see that we have not discussed the stacked bars from the diodes array, because that will be a little bit more complicated for as far as this lecture is concerned. So this is the end of slide number 100.